Hello and welcome to Educator.com and welcome to the first lesson of physical chemistry. Before I actually launch into the physical chemistry, I wanted to talk a little bit about the course as a whole so that you have an idea of what it is that you're in for, what it is to expect. So physical chemistry is taught in two ways. We teach classical thermodynamics first, and then we teach quantum mechanics, and then we go back and teach statistical thermodynamics. In other words, we go back and we use quantum mechanics to explain what we learned in thermodynamics. The other way that it's taught, and it seems to be becoming more and more popular these days, it's quantum mechanics first, and then statistical and classical thermodynamics are sort of done simultaneously. This particular course does classical thermodynamics first, so I go with the first method. Classical thermodynamics first, it goes on to quantum mechanics, spectroscopy next, and then finally statistical thermodynamics. Now, many choices have to be made in a PChem course about which topics to cover. The more topics one covers, the less time one has to cultivate a fuller understanding of the fundamentals. In other words, time is finite. If I spend more time on this, it's more topics, but it gives me less time to sort of assimilate what it is that I've learned before. I have always been one who believes that it is more fruitful to read 3 novels closely and deeply than to have read 20 novels and, for the sake of impressing, be able to enumerate 20 novels. You get a lot more out of doing less, but doing it very, very well. That's always the case, always the case, always the case. And if you ever run across a situation where you have to make the choice, I promise you, if you make the choice of doing fewer things but doing them well and deeply, it will be a lot better than having done multiple things. It's just the way the mind works. It's just the way discipline works. It's just the way true deep learning actually works. I've chosen what I consider to be the most important topics for a strong foundation. If, after further reflection, I feel that what I have left out deserves to be covered, or if there is a clear demand for a topic that I have left out, I will absolutely be happy to go to add that topic to the course, however many topics that might be. If what I have presented in the course is understood to a reasonable degree, then any topic that I have left out that your particular course does cover, it should be reasonably easy to follow. In fact, it should be very, very easy to follow. I've presented a solid, good foundational course. Okay, this course is a very important part of your scientific literacy. It is a first exposure to pulling back the curtain and exposing what's actually going on. I hope that you find it as beautiful as I do. Best wishes, and let's jump right on in. Okay, so we're going to start with the ideal gas law. So mostly what we're going to be talking about is gases. We will talk about liquids and solids occasionally, and we'll see a couple of them in the problems, but gases is going to be what we are most concerned with. So let's begin with the ideal gas law. So the ideal gas law, you know it as PV equals nRT. The pressure, given a gas, the pressure times the volume equals the number of moles times the gas constant times the temperature in Kelvin. That's it. Nothing more than that. It is an equation of state. It is an equation of state. And you're going to hear that term a lot. It is an equation of state. What that means is the 4 variables pressure, volume, temperature, and N, the number of moles, describe completely the state that a particular gas is in at a given moment. Describe the state of a gas. Okay, let's talk about units. Units are going to be very, very, very important in this course. In fact, probably the single most annoying, tedious thing that you're going to have when you deal with your problems is remembering to deal with the units and converting the units. It makes all of us crazy, but there it is. Okay, so let's talk about units. Well, the SI unit of pressure So the SI unit of pressure is the Pascal. Symbolized PA. Okay, pressure is defined as force per unit area. So when I have the amount of force, if I divide it by the particular area over which I'm applying that force, I get the pressure. So pressure equals F over A. Well, unit of force is a Newton, and a unit of area is a square meter. So 1 Pascal equals 1 Newton per square meter. From here, we can go ahead and manipulate the units to serve our purposes. From here, excuse me, we can manipulate units as necessary to move between equivalent unit expressions. And if you ever lose your way in a problem, and I actually talk about this more when I actually do the problems, if you ever lose your way in a problem, think about the units, and that will sort of, in fact, help you solve the problem in many of the cases, particularly in classical thermodynamics, to move between equivalent unit expressions. Okay, so let's go ahead and actually stick page for page here. So we have 1 Newton per square meter. Well, a Newton is a kilogram meter per square second per square meter. So we have 1 kilogram per meter square second. Yes, there we go. 1 Newton per square meter, which is a Pascal, is equal to 1 kilogram meter per square second per square meter. If I multiply by meter over meter, I end up with 1 kilogram meter squared per second squared per meter cubed, and that's equal to 1 joule per cubic meter. So 1 Newton per square meter, which is 1 Pascal, is also equal to 1 kilogram per meter second squared. It's equal to 1 joule per meter cubed. That's it. I'm just manipulating units. Excuse me. Okay, so I have 1 atmosphere of pressure is equal to 1.01 times, well, you know what, 1.01325 times 10 to the 5th Pascal. This is exact. And I have 1 atmosphere is equal to 760 torricelli. That is also exact. Now, the millimeter of mercury, Hg, is actually bigger than the torr by a factor of 14 parts per 10 to the 8th, which is clearly insignificant. So, but we take 1 millimeter of mercury equal to 1 torricelli. Okay, the SI unit of volume. The SI unit of volume is, so we just did the SI unit of pressure, now we're doing the SI unit of volume, is actually the cubic meter, not the cubic centimeter. In practice, we use cubic centimeters and we use liters. Okay, 1 liter is 1 cubic decimeter equals 1,000 cubic centimeters equals 10 to the negative 3 cubic meters. So 1 liter is 10 to the negative 3 cubic meters. This is exact. Go to the next page. The SI unit of temperature is the Kelvin. That's it. K. Y'all know that already. Okay, the value of R, the gas constant. PV equals nRT. R equals PV over NT. P0, V0 over N0, T0. If I take, let's see, so R, if I take the pressure to be 1 atmosphere, well, let's do it this way. Yeah, that's fine. I'll just write out what it is that I have here. So P0, if we take 1 atmosphere as our base, which we said is 1.01325 times 10 to the 5 Pascal. If I take my initial volume, or basic volume, to be 22.41383 liters, and if I take N to be 1 mole, which is going to be 22.41383 times 10 to the negative 3 cubic meters per mole. Again, we're trying to stick with SI units. Temperature equals 273.15 Kelvin. Therefore, if I put all of these values in for P0, V0, N0, T0, sticking with cubic meters per mole, pascals, I end up with R equal to 8.31441 Pascal cubic meter per mole Kelvin. Now, recall that 1 Pascal equals 1 joule per cubic meter. So 1 Pascal cubic meter equals a joule. So Pascal meter is a joule, therefore R is equal to 8.31441 joules per mole Kelvin. That's where all this stuff actually comes from. Joules per mole Kelvin. Now, if I want it in liter atmosphere per mole Kelvin, I get 0.08206. Actually, I'm going to give you the full number here, 0.058. That is liter atmosphere per mole Kelvin. Now, if you wanted an equivalent expression for joules and liter atmospheres, just use this conversion factor right here. So if you want an equivalence between J and liter atmosphere, and you will, then 8.31441 joules per mole Kelvin times 1 mole Kelvin is 0.08206 liter atmosphere. Mole Kelvin cancels mole Kelvin, and I'm left with 101.3 joules per liter atmosphere. How's that for a conversion factor? Okay. Okay. So keep a very, very close eye on units and conversions. It's going to be very, very important for this course. All right. Now let's talk about, I think I'm going to go to black here. Let's talk about extensive and intensive variables. Extensive and intensive variables or properties. Variables or properties. Okay, so let's start off with the ideal gas law. PV equals nRT. Okay, an intensive property. An intensive property, the two intensive properties in this are pressure and temperature. And the reason they're intensive is that they do not depend on the amount of a substance. Amount of substance present. So an intensive property, an intensive variable, is one that actually does not depend on the amount of it present. An extensive, the extensive properties here are volume and the number of moles. They do depend on amount. They do depend on the amount. Okay. Let me see if I want to, total mass, mass is another extensive property because the amount of mass depends on how much you have. If you have 3 grams of 4 grams, it's going to make a difference. So mass is an extensive property. If I take 1 mass of iron, if I take 1 gram of iron and if I take 10 grams of iron, both sitting on the same table, well, the temperature is going to be the same. So if I measure the temperature of the 1 gram and the 10 grams, it doesn't matter how much is there. The temperature is intensive. It has nothing to do with how much iron is there, but the mass does, the volume does, number of moles does. That's the difference between the two. Okay. Let's see. Okay, this is very, very important now. The ratio of two extensive variables always gives an intensive variable. So, for example, our example is going to be if I have mass, which is an extensive variable, and if I have volume, which is an extensive variable, if I take the ratio of the mass to the volume, I get the density. The density is an intensive variable. 1 gram of iron, 10 grams of iron, the density of iron stays. 1 gram of iron has a certain volume. 10 grams of iron has a certain volume. Those are extensive, but if I take the ratio of those two extensive, I end up with an intensive variable. That's very, very deep, very profound, and very important. Density, intensive. So I repeat, the ratio of two extensive variables always gives an intensive variable, and we will often do that. Okay, now let's go ahead and take a look at PV equals nRT. Okay, so we have PV equals nRT. I'm going to divide both sides by n. Okay. So I end up with PV over n equals RT. Now, I'm going to rewrite this as, well, basically what I'm going to do is take this. I'm going to take whatever volume, which is an extensive variable. I'm going to divide by n, which is also an extensive variable. They're both extensive. The ratio of two extensives gives an intensive. I'm going to rewrite this as P, V with a bar over it equals RT, where V bar is just equal to V over N. I've taken the volume and I've divided by N. It's called the molar volume. Volume per mole. Okay, now the ideal gas law. Now, the ideal gas law, written that way, consists of all intensive variables. Of all intensive variables. Okay. So, okay. Now we can discuss gases and their properties without worrying about whether there is 1 mole or 50 moles. Now the amount doesn't matter. When amounts don't matter, that's when we begin to uncover and elucidate underlying truths. So now we can discuss gases and their properties without worrying about whether we have 5 moles or 50 moles. It's not going to make a difference. So any fundamental property of a system, fundamental property of a system, should never depend on how much is there. Never depend on how much is there. As I said, we wish to elucidate general truths. In any specific case, we might deal with the amount. But when we talk about generalities, we never talk about the amount. We shouldn't have to talk about the amount. It should apply to every situation across the board. Okay. Now, so in general, volume is not the only thing that you see with a line over it. So in general, any variable with a line over it is a molar quantity, In other words, it's been divided by the number of moles that are present. Molar quantity, meaning it has been divided by n, the number of moles. Okay, so now let's talk about being able to graph equations. So graphing equations. Well, clearly graphing equations is just insanely important in science. So let's go ahead and start with our PV equals RT. This is a relation among 3 variables: pressure, molar volume, and temperature. This is a relation among 3 variables. Okay. If any 2 are known, the third is automatically known. If any 2 are known, the third is automatically known. Okay, let's solve for each variable separately. We're going to solve for P, we're going to solve for V, and then we're going to solve for T. So let's start by solving for P. So P is equal to RT over V bar. I'm going to write it as RT times 1 over V bar. Okay, this 1 over V bar, these are hyperbolas. Now, I'm going to hold temperature constant, and then I'm going to graph pressure versus volume. Holding T constant, very, very important. Holding temperature constant. We graph P versus V bar. In other words, P is on the y-axis, and V bar is the x-axis. Okay? As the molar volume changes, gets bigger, what happens to the pressure? Or as the pressure gets bigger, what happens to the volume? Here's what we get. Okay, this is the pressure. It's going to be in atmospheres. This axis is going to be molar volume. It's going to be cubic decimeters per mole. Okay, molar volume. What you get when you graph this equation by holding T constant, you end up with this. You end up with a bunch of hyperbolas. This is the one for, let's say, 100 Kelvin. This is one for 200 Kelvin. Again, I get different graphs, different lines, different curves, one for each temperature that I'm holding constant. Okay? I'm holding temperature constant, I'm changing V, I'm seeing what happens to P. This might be 400 Kelvin. So clearly the whole thing, there's an infinite number of these. So note, for a given V, for a given volume, okay, for a given volume, a higher temperature means a higher pressure. Means a higher pressure. You already know this from general chemistry. A higher T means a higher P. That's it. That's what's going on. Okay. Let's forward again. Okay. Now, every point in the PV graph or in the PV plane, every single point in that two-dimensional plane represents a particular state of the gas. Represents a particular state of the gas. In other words, it represents a particular pressure, a particular volume, and a particular temperature. Represents a particular state of the gas. By holding the temperature constant, by holding the T constant, I constrain the states to follow a curve. All right? Here's my P. Here's my V. I have a bunch of different temperatures. Once I actually choose a temperature, now, as I change pressure, as I change volume, the change is going to follow that curve. It's not just going to bounce around. It's going to follow that curve. For a different temperature, it's going to be another curve. For another temperature, it's going to be another curve. Now, when I make changes, it goes up and down along that curve. These curves, for this particular graph holding temperature constant, these curves are called isotherms. And isotherm just means equal heat. That's it. That's all it means, equal heat. In other words, holding temperature constant. So in thermodynamics, when you hear the term isothermal, that means I'm keeping the temperature constant. That's all it means. Are called isotherms. These curves are called isotherms when T is held constant. Okay. Well, let's start again with PV equals RT. This time let's go ahead and solve for volume. Well, V is equal to RT over P. I can write this as R over P times T. Well, that's interesting. This is linear. Okay, T. Now I'm going to hold pressure constant. Now, let's hold pressure constant. This is constant. Well, R is already a constant, so now I'm going to graph V versus T. And express V as a function of T. Here's the graph that I get. This is my volume. This is my temperature in Kelvin. This is linear. Okay, I hold P constant at different pressures. This is what it looks like. This one might be 3 atmospheres. Let's say this one is 2 atmospheres. Let's say this one is 1 atmosphere. That's it. So now what I've done is I've expressed this PV equals nRT. Now I've graphed volume versus temperature, and at different pressures that I choose to hold constant, I have these lines. When I hold pressure constant, these lines are called isobars. So now, if I pick a particular pressure, 3 atmospheres, if I raise the temperature, the volume is going to travel along this line. It's not just going to be everywhere. At 2 atmospheres, if I change the volume, if I change the temperature, the volume is going to travel along that line or go backwards. If at 1 atmosphere, it's going to travel along this line. This is a state, 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 for a given volume, for a given temperature, and for a given pressure. These lines are called isobars. So, when pressure is held constant, the lines that you get are called isobars. When pressure is held constant and you have volume versus temperature, those are called isobars. Okay. So, note, as the pressure rises, of course, R over P, the slope decreases. That's why, from your perspective, as the pressure rises, the line gets closer, becomes more flat, closer to the x-axis. Okay. The slope decreases. Okay. Let's start again with PV equals RT. This time, let's go ahead and let's see. Pressure. Now let's try this. So let's go P equals R over V T. Looks like an interesting P here. Actually, let me just check one thing, make sure I didn't T over V. Yes, not a problem. Okay, so P equals RT. Oh, write this again. So pressure equals RT over V. Okay, now before we did, we took RT and we held temperature constant. Now I'm going to take R over V times T. Now I'm going to take R over V separate times T. So again, we get a linear graph. And now what I'm going to do is I'm going to graph pressure versus temperature, but I'm going to hold the volume constant. And what I get here is this kind of graph. Pressure, temperature, different volumes. So I get, once again, I get something linear. Boom, boom, boom. This one might be 30 cubic decimeters per mole. This one might be 20 decimeters per mole, cubic decimeters per mole. This one might be 10 cubic decimeters per mole. Again, we're talking about molar volume. So whenever I have these, whenever I have a pressure temperature graph for a particular volume, if I change the temperature, my pressure is going to move along this line. These lines are called isochores or isometrics. So for constant volume, for constant molar volume, we get, let's move on to the next page here. We get things called isochores or isometrics. Lines of constant volume. That's it. So let's go ahead and draw this all out here. Let me see. Yes. So I've got P equals RT over V bar. I've got V equals R over P times T, and I've got P equals R over V. All my variables are going crazy. R over V times T. This graph, I ended up with hyperbolas. This was where T was held constant. And these were called isotherms. Here, we had V along this axis, so this is P along that axis, and this is going to be V along that axis. This is V along this axis, and this is T along this axis. I ended up getting these things. These were called isobars. In this case, I held P constant, basically the thing that you're taking with the gas constant here, RT over V. These are the variables, hold that other thing constant. V and T are the variables, hold the other variable constant. Here, it's P and T, hold the other variable constant. Now we're going to hold this constant, and again, here we have pressure, here we have temperature. Again, we ended up with a bunch of these, and these are called isochores. Okay. Now, let's see. How do I want to do this? Okay. So let me take a look at this one right here. So this one, this was molar volume versus temperature. Okay, so this equation here, which was molar volume equals R over P times T. Okay, this equation, when I look at these pictures, this equation and graph is easier to see. As temperature drops to 0, it's telling me that the volume is going to drop to 0. This equation and graph, they imply that at T equals 0, the molar volume equals 0. Okay, this doesn't happen to real gases. Okay, but this does not happen for real gases, and here's why. Well, gases, as T decreases at some value of T, the gas actually liquefies, turns into a liquid. The gas liquefies. So, a further drop in temperature, does not change the volume. Once something is a liquid, the temperature, that's it. It's just going to stay at that volume. Okay. A further drop in T does not change the volume, does not decrease the volume. Decrease the volume. In other words, this is an ideal gas would behave this way, but real gases liquefy at low temperatures. Therefore, the graph itself, real gases, they don't go to 0. Okay, now the first equation that we did, which was this one, where we had pressure and where we had the molar volume, this equation and this graph, which was P equals RT over V, and 1 over V was, or V was the x-axis, these imply that as pressure increases, as I go up in pressure, it implies that the volume actually goes down to 0. Okay? As P increases, that the volume goes to 0. But again, that doesn't happen. At a certain pressure, at a certain P, the gas liquefies. That's it. You're just squeezing all the gas particles together. At some point, boom, they get so close, they just turn into a liquid. The gas liquefies. So no further increase, excuse me, so no further increase in P reduces the molar volume. Okay, let me see. This is called isothermal compression. Isothermal because you're moving along an isotherm. These are called isotherms. You're compressing it. In other words, you're increasing the pressure. As you're increasing the pressure, what's going to end up happening, the volume is going to, of course, get closer and closer and closer to 0, but at some point it's just going to liquefy and it's not going to go any further. Hence the ideal gas. That's why we call it the ideal gas law, not the real gas law. Hence an ideal gas. Okay, now, at low pressures and high temperatures. At low pressures and high temperatures, the ideal gas law is actually very accurate, profoundly accurate, in fact. The ideal gas law is quite accurate. accurate at describing gaseous behavior. So, deviations from ideal behavior occur at high pressures and or low temperatures. High pressures and or low temperatures. In other words, as the molecules start to get really, really, really close to each other. So, and we'll talk about that more in subsequent sections. Okay, so thank you for joining us here at Educator.com. We'll see you next time for a continuation of classical thermodynamics.